Okay, thanks everyone. So our next speaker is Sennesh, who's going to be talking about string diagrams with factorized densities. Take it away.
All right, hello everyone. I'm coming from Northeastern University up in Boston, and the talk is pretty much going to be exactly what it says on the tin. So first the motivation, which is that up at Northeastern, at least in our lab, we are in some technical sense statisticians or machine learners. And in statistics, this being a very applied area, we need probability densities for things. Why? Because when they give you a data set, it's a big scattering of points into space. It doesn't really usually form a measurable set under a sigma algebra if you're not working in a countable sample space. So rather than being able to evaluate a measure over it, what you actually want is a density, which intuitively means something like the derivative of a measure around a point. In particular, what we really want is in some sense a likelihood, which is a probability of the data given a parameter. You might be integrating out a latent variable, etc., etc. So the goal here is to say we draw a string diagram in a copy, delete, or Markov category like we've been talking about all week in a lot of the talks. And we know that we can fill it in with a probability density. So the applications are going to include categorical cybernetics, probabilistic programming, structural causal models, things we've all heard about quite a bit actually. So similarly, there's a lot of related work. You can read into the background on Markov categories. You can read Tobias Fritz's team's work about generalized causal models in copy, delete, and Markov categories. When I want to formalize something concrete, I'm going to be using the notion of push forwards as densities of S-finite Markov kernels. That's Sam Statton's work. And then, of course, there's quite a lot going on in categorical Bayesian inference right now, and this will contribute only a little more. So the abstract setting, we've been seeing this all week. Copy-delete categories, SMC, in which every object has a comonoid structure that commutes with a monoidal product structure. Markov category makes the comonoidal co-unit natural, so that effectively you take any Markov kernel or you take any process or morphism in a Markov category, post-compose it with delete, and it just becomes the unique map into the terminal object. Then we have this notion of a deterministic subcategory in a Markov category. Categorically, this is defined as morphisms which commute with copy. More intuitively, it is defined as things that are not probabilistic or that define conditional delta measures. Well, I guess my intuition, sorry. So as a concrete setting for categorical probability that I just happen to be using here, you can swap it out and use your own if you like. We're going to work with the category of measurable functions between measurable spaces. Objects are sets with sigma algebras. Morphisms are functions whose pre-images on measurable sets are themselves measurable sets. Then as a further concrete setting, we're just going to have stock. This is the result of applying the Geary monad and taking the Kleisli category. So you're going to map measurably from a parameter space into a space of probability measures. All right, so let's actually just headline the point of the paper before giving you all the mathematical details. Here's a recipe for this thing I'm calling a joint density kernel. You're going to pick your domain and codomain. Now you're going to pick a residual, which is a set. It's sigma algebra and an sigma finite measure over it. This has to be a standard Borel space. Now you're going to say, all right, now that I have a residual and a base measure for the residual, I will pick out a conditional density function like I actually wanted to work with this whole time. and I can integrate it over a measurable set in order to actually get the Markov kernel that I want to work with. Then I'm going to pick a push forward, which is in the deterministic subcategory of my Markov category, and the push forward is going to take both the residual and the parameter, and it's going to produce an output. And then I'm going to arrange them into this little diagram here. You read it from top to bottom rather than bottom to top, like some of the talks we've seen. And you can sort of imagine bending the diagram sideways, which I wasn't able to draw, so that Z comes from the left, X goes to the right, and M goes downward, and you can imagine a nice bicategorical view there. So really, this is just a formal way of saying everything I just told you. You take your Z and your X, which are in stock. You take F and a base measure on its codomain. That's going to be in a semi-category or sieve of density kernels, I call them. You take your push forward, which has to be deterministic. You make sure that your residual is a sigma finite standard Borel measure space. It really is quite a mouthful. You package them together, great. Now you have a morphism in what's going to be a copy delete category diff joint between Z and X. That's it. So these will then eventually be seen to form a category because they form a wide subcategory of the copy delete category joint, which is given in the paper. Really, joint is just a way of talking about this particular form of diagram that I drew before you get into the need for base measures and densities. So you can basically say, if I have a residual in the middle that I'm going to co-parameterize with, that's joint. If I then have to have a density over the residual, that's diff joint. In order to verify that this all forms a category, we're going to show how to compose it. Basically, after you perform your push forward, you can then apply the stochastic Markov kernel from the second morphism, tensor together your residuals, just perform one little swap so that you send the right residuals to the ports of the push forwards, and voila. Similarly, all you have to do is one little swap in order to form the tensor product of two joint density kernels. All right, so after looking at a bunch of symbols, let's work with some examples perhaps. This is an example taken from Rudul and Alexeev. What they do is they say, all right, you're going to give me a 2x2 matrix representing a linear transformation T. I'm going to sample an angle from the uniform circle. So really a uniform distribution between 0 and 2 pi measured in radians. Then I'm, of course, just going to turn the angle, which is really a polar coordinate on the unit circle. I'll convert it into xy coordinates. And then I will actually, and then I will multiply it by my transformation. There's actually a bit of a typo here where it should be R2 as the output, but anyway. Now you have a stochastic point on the circle. And since you have this transformation T, the point here is that if it's if it's a transformation other than a scaling, then you don't just have some scaling of the uniform density function. So here's where it's actually useful to say, on the left, I have how I write this in diff joint. It's just one box in a diagram. And it does show both copies of R. Good. So the typo is only on the right. Then, oh no, both copies of R are shown in both places. Great. It's not actually erroneous. Shows what I get. But and then you can convert it into this thing on the right. where what you would be able to do is, if you wanted to, you could just delete both the real numbers, the x and y coordinates, and you would have a probability density that you actually know about over 0 and 2 pi. Or sorry, over the interval between 0 and 2 pi. Whereas if you applied del to the interval between 0 and 2 pi, that would count as marginalizing out the intermediate randomness. Then you have a Markov kernel from R2 by 2 to R2, and this would not necessarily support a density, depending on what kind of transformation you passed in, or rather, it would have a, let's say, a non-standard density, since you would basically have to warp the base measure geometrically instead of just giving the Lebesgue measure. And yeah, you could actually calculate the density for that based on how the transformation warps the coordinates. So a slightly more involved example where we're going to see that there isn't a density once you marginalize out the intermediate residual. So we have some coins. We want to detect a counterfeit. It's very old times, and so rather than just dropping some solution on them to perform a chemical analysis, we're going to check their mass. We put the coins one by one on a well-calibrated balance, left, right, left, right. Now we have some prior belief. P is distributed according to the Bernoulli distribution with, a 50-50 chance of there existing a counterfeit coin. Now we're actually going to perform a case analysis. If my prior belief is that there is a fake coin, that is, if I flipped my coin and it came up true, well, yeah. In the one case for P, then the balance will show a meaningful difference, which will be normally distributed. Let's say it's about 5 centimeters on average between one side of the balance and the other that is skewed, if there's a fake coin. If there is no fake coin, then the balance will, well, it'll balance perfectly. So that'll be a delta distribution over 0 centimeters of difference between the two sides. Now, again, on the left, I can basically just display this as 2 boxes. One comes from the terminal object and just gives me a state. The other has a conditional that includes my case analysis. And what I get out is the difference between the two sides of the balance that I actually see, my observation. But on the right side, what I actually see is that really I'm taking a direct sum, or depending on which category you're working in, it's either a coproduct or a direct sum. I'll explain later. Point being, what I actually have is a pairing of 2 morphisms, one being the Gaussian and the other being the delta, and these actually have different base measures. So now, by coparameterizing and saving all these residuals as outputs of my morphism, I'm ensuring the existence of a density over the residual space by actually remembering what its base measure was. I'm still eventually going to have, I'm going to pass the result of that residual through my co-pairing here and eventually just get a real observation. But now I've broken up the second part of the case analysis into the unit, which has a trivial density. It's a Dirac delta probability measure, which has a density with respect to the counting measure. And the delta in the co-pairing, which is still deterministic because it's a delta, but now is sort of passing from the monoidal unit into the real numbers. So it's a state instead of a conditional or a channel. If I had actually marginalized out my intermediate residuals here, the resulting marginal measure on R is actually known to lack a density with respect to the Lebesgue measure. Specifically because one of the components of it, if you take, effectively, if you decompose it piecewise, one of its components is just a delta measure, which cannot have a density with respect to the Lebesgue measure. On the other hand, the residual has a joint density just fine that even breaks down into nice conditional factors. So now let's just get into some of the concrete math on how this works. The theorem that tells us when probability densities exist is just the Radon-Nikodym theorem. I'm giving the common formulation of it here, just shifted over to measure kernels instead of measures. So consider two sigma finite measure kernels, mu and nu. Both of them have the same domain and codomain. We assume that nu is absolutely continuous with respect to mu, which means that it has at least the same null sets as mu, possibly more null sets. And then we can say that at every parameter there's going to exist a Radon-Nikodym derivative, quote unquote, or simply a density function, which can be evaluated pointwise over the codomain, and it's integral over a measurable set. When we take that integral by integrating with respect to the base measure mu, will give us the measure kernel nu. Now, what we often want to have non-trivial, so to speak, non-trivial densities, if we just set nu equal to mu, so you have mu and mu, of course there is a Radon-Nikodym derivative of any measure with respect to itself. Sure, okay. What you actually want is to have a base measure that is in some sense nice. Specifically, it's going to be sigma finite, meaning that a countable sum of subcomponents is going to cover your entire space. Each of those subcomponents has to assign finitely much measure. And ideally, it should be translation invariant, meaning that in some sense you can move the measure over the space and the measure doesn't change. For the counting measure and the Lebesgue measure, this is relatively intuitive. There are nice results showing that if you're working with something like the real number line, the Lebesgue measure is the unique nice measure with these properties. So then, why didn't we have densities before? Well, it turns out that conditional density functions are just a semi-category. Specifically, there is no identity density. You have to pick your poison and fail one of the several conditions of the Radon-Nikodym theorem. So the identity morphism in a Markov category, or really in stock, Borel stock, Kleisli of Geary of QBS, name your example, is going to be the conditional Dirac delta measure. It has absolute continuity with respect to the counting measure. The counting measure just returns the number of points in a set. However, this means that the counting measure is not sigma finite on the real line. Notably, the counting measure is sigma finite on the natural numbers, the integers, or another countable set. But really what we're saying is you need a base measure that is appropriate to the cardinality of your sample space. And if you don't have one, you fail Radon-Nikodym. There is no density. So the way that I ended up fixing this was really just to follow the recipe that I showed before, but give it its own proper definition and say, all right, let's have Hom sets for this semi-category. They're going to consist of pairs of Markov kernels with sigma finite base measures. In order to just make sure that everything goes through and we can generalize later, we're going to assume that all of these residuals are standard Borel spaces, or rather that the residuals are into standard Borel spaces. I'm going to show you how those are constructed in a bit. They're actually quite nice. And we'll assume that there's absolute continuity at every parameter. Hooray. Since the only thing that really failed to form a category was identity, tensoring and composition work nicely, and it's almost like you could say a Markov semi-category. So the base measure is actually the troublesome thing to get right, especially because, as the reviewers pointed out for this paper, there's quite a lot of measurable isomorphisms. And what that means is that you can't just say, well, here is my measurable space, here is a measure, and then let someone freely apply morphisms to your space, because they might apply an isomorphism and now it's a different space and your base measure hasn't changed. So what we end up actually having to do is restrict to the category of measure spaces, then the subcategory of standard Borel measure spaces, and then restrict even further to conditions that give you only the sigma finite standard Borel measure spaces. Try saying that 3 times fast. I certainly can't. But the actual fun thing is that really when you get down to it, this is just 2 spaces, the singleton space, the Lebesgue measured reals, and then direct products and direct sums of those. That's it. So given a whiteboard over here, I could actually write down, a very nice endofunctor, and we could talk about its algebras and coalgebras, and that's sort of in the future work. So I think it is sort of, in the end, even if we're restricting to standard Borel spaces, just to have all the random variables that us probabilists want. So anyone working in a somewhat more sophisticated domain is going to have to do a bit of their own math here. Nonetheless, I think it can boil down to something simple and elegant. All right, so then we'll finally give some proper formal definitions for things like joint. And as you can see, we're just going to take a Markov kernel in stock into our residual. Then we're going to have a parameterized deterministic morphism. So it's going to be a deterministic morphism of Z tensor M into X. And that those nice little fancy double brackets I showed you earlier are actually symbolizing a full Markov functor that sends morphisms in joint or diff joint into copara stock so that we can actually, explicitly work with the diagrams and bicategorical structure like we want. So that's pretty much the end of it. But there's a few ways I think this could actually be improved mathematically. One would be take this idea of something with a density or a push forward thereof and put it really into a proper Markov category instead of a copy delete category, because joint and diff joint are only going to form copy delete categories. They don't have a terminal object with a unique morphism into it. So they're not semi-Cartesian like a Markov category should be. And really, the probabilist in me thinks that, as I describe in point 2 here, what we would really, really like is to get a Lebesgue decomposition theorem, or a restriction on the results of the Lebesgue decomposition theorem, that would basically say, you have to give me a Markov kernel that Lebesgue decomposes into something nice, in the sense of something with a density, push forwards of a thing with a density, an atomic measure, and no other nasty stuff. And if you want to talk after, I can tell you what the nasty stuff is, but suffice to say that measure theory has some fun counterexamples to nice properties. Then similarly, there are suggestions in other people's work that if you're considering a smooth manifold as your sample space, then you could actually just standardize on the Hausdorff measure, which generalizes the counting measure and the Lebesgue measure to both fractional dimensions, higher dimensions, etc. And then, of course, if you still ultimately want to work on standard Borel spaces, then besides just baking the base measure into the definition of an object, so that it can't be changed by a measurable isomorphism, one thing you could do is just consider the endo functor that says, here's my two base cases, the singleton and the reals. Here's their countable direct sums and their finite direct products, and consider algebras and coalgebras on that sort of thing. So for applications, I would say a nice thing about working with Markov categories is that if you have randomness pushback, then you can pretty much turn any morphism in any Markov category into the moral equivalent of a structural causal model. Probabilists call randomness pushback the randomization lemma. It is known to apply in Borel stock, and it applies by construction in the Geary monad of quasi-Borel spaces. At this time, I don't think it's known whether it applies in full to stock, hence why I didn't just use it. Similarly, you could take all the constructions I gave here, generalize them beyond stock, work with quasi-Borel spaces, quasi-measurable spaces, some other nicer alternative that you might want, or you could just work with their image under adjoint functors in stock. The thing I'm excited about is actually optics for causal models with factorized densities, and then bicategorical structure of approximate Bayesian inference. Approximate in the sense that not only do you have to have a density function, as in a Radon-Nikodym derivative, you need to be able to write it down in algebraic closed form and calculate with it. All right, and I think that brings us to the questions.
Okay, thanks very much. Yeah, we got about 4 minutes for questions.
Actually, can I say one more thing?
Yeah, go for it.
Sorry, and I ran out of space in the talk, but if you read the paper, you will see that, yes, there are theorems showing that when we talk about these diagrams forming causal models, like this copy-delete category joint and diff joint, you know, you can factorize them with generalized causal models as given in the literature. They're not special in that way. It's not like they fail to have causal models.
Okay, right. Any questions here? Is that no? Yeah? Sorry, I thought you had your hand up. Yeah, yeah? Okay.
Hey, thanks for the great talk. Yeah, the echo is a bit weird, but could you expand on your remark on why you might want to sort of like have a bi-category or like a second direction for one of the outputs?
Yeah, so without giving anything away that I haven't already pre-printed, right? But so in approximate Bayesian inference, often what you'll have is one probability distribution that is easy to sample from, call it a proposal, and another that is hard to sample from, called a target. Often an important property of the target is that you only know it up to its normalizing constant. So you can evaluate a density for it, but the density is unnormalized. If you knew how to integrate that density in closed form, it might not integrate to 1. So then what you have to do is find some way to take density evaluations or samples with respect to your proposal and turn them into samples from your target. And there's a whole class of, I would say, like sampling strategies, weighted sampling strategies, message passing strategies, a whole variety of ways to construct these approximations. And what I would want to do is basically say, all right, let me have a bicategory where the vertical dimension, or let's say the horizontal dimension, is generation in the ordinary like Markov category sense. And the vertical dimension is actually a change of measure that passes from targeting one thing to targeting another.
Okay, time for one very quick question. Anything left? You're online. Yeah, okay, maybe this isn't quick enough, but I was just wondering that you had these examples where often the marginal doesn't come with a, loses the density, basically. Maybe you feel like you've just already, but is there like a really easy way to see that sort of diagrammatically what's going on there? Because I know you can, I guess related is the idea that you can, if you work beyond the Markov category, you can actually draw the densities like as kind of effects and things like this. I don't know if it would help with that.
Sorry, could you repeat the question, actually?
In these examples where you had one of these joint densities, but then when you take the marginals, you lose the density, right? Is there like a easy way to see that that's going to happen diagrammatically, or is it kind of specific to what's inside the boxes so much that there's nothing to say about it diagrammatically?
So, I'm not sure how helpful reasoning diagrammatically would be there. Type checking of a sort is helpful there in the sense that if you try to have essentially basically if you don't wholly replace the original base measure, but instead you restrict it, you're going to lose density. Like you're going to lose Radon-Nikodym. So in that instance where you have, say, a Bernoulli, and then you have a mixture of a Gaussian and a delta, well, that mixture has two different base measures. And so if you just box it up as a pairing inside of a Markov kernel, and then you say, well, really this is just a Markov kernel from, 2 into the reals, then what you've really done is you've said, well, it's from 2 into the reals, but the reals with what base measure? Like a non-stand, the reals with a base measure that is, the reals with a base measure that decomposes by the Lebesgue decomposition theorem into a nice Lebesgue component over here and an atomic component over here, but with respect to which both of the probability measures are going to fail absolute continuity.
Okay, let's thank Eli one more time. Okay, thanks very much, everyone. Let's thank all of our speakers one more time.